All right, so let's get back to the second part of the lecture. And we needed to talk here about directed MAXSAT resolution, which is a method that uses the resolution step we mentioned to systematically solve a MAXSAT problem. This is very similar to directed resolution in the sense that you pick a variable ordering and then you apply resolution according to that variable ordering. It's pretty much the same, except that we will avoid resolving two clauses on a variable if they also, because if you're resolving on xi, that means one of them has xi, the other has not xi. So we will not do that if they actually contain complementary literals on some other variable. Actually, we also omitted these in regular resolution. So it's pretty much the same procedure, except what's interesting here is the guarantee. So when we finish this, we do it all the way, and the guarantee that you have is the following. So when I say we do it all the way, that means we don't stop when we find an empty clause, we keep going. So more generally, when you finish this procedure, you may end up having a bunch of empty clauses. Let me write these as false. And then you end up having the rest of the clauses, let's call them delta. And let's say that we have, in this case, k of these, k empty clauses. And let's say this is the situation when you're done, okay? You have derived k empty clauses, and this is the rest of the clauses that do not have an empty clause. Now, the guarantee you get is the following. It's twofold, which is pretty interesting. The first one of them is basically k is guaranteed to be the minimal cost of any world or any variable assignment. So you cannot do better than this. That means no truth assignment will have a cost less than k. It will be either k or more. And the other more interesting thing is that this delta, actually, maybe I should make this gamma here so that it's different from the original delta. This guy is guaranteed to be satisfiable. And moreover, every world that satisfy gamma has cost k. Okay, this looks pretty interesting, right? So I do run directed resolution, but directed MAXSAT resolution. And at the end, I do have a k number of empty clauses and the rest. The number of empty clauses that I discover tells me the cost of the optimal solution, and the remaining clauses characterize those solutions, those optimal solutions. So if we're going to take an example of that, but we're going to apply it to this guy, which is here. So if you take that and under the variable ordering A, B, C, and apply directed MAXSAT resolution, what's going to happen in this case is that you're going to end up with the following. You end up getting one empty clause, and then you end up getting two other clauses, which are these guys. Let me write them. Okay, this would be the output. And what does that tell us? That tell us, if you look at the original knowledge base with 4 clauses, each one of them has a weight of 1, and you apply directed resolution, you get this. That means no variable instantiation, right? I have 3 variables, that's 8 variable instantiations. No one will have a cost less than 1. That means you have to violate 1 clause, at least. And moreover, if you look at these 2 clauses here, every variable instantiation that satisfies these 2 clauses will have a cost of 1, all right? So this will characterize your solutions. In fact, if you look at the table, and that is shown in your chapter, if you look at the table over the variables A, B, C, you're gonna find that there are basically 6 instantiations that satisfy these 2 clauses, 6 out of 8, and all of them have a cost of 1. And the 2 instantiations that do not satisfy these guys are the ones where you have 1, 0, 0 and 0, 1, 1. Both of these do not satisfy this, and each one of these will have a cost of 2. But all of the others will have a cost of 1. And those guys satisfy gamma, do not satisfy gamma. And this is our gamma here. All right. Of course, we didn't apply yet directed resolution to this. We'll just do this in a second, and that will basically close this discussion. But I wanted to show you the final guarantee first before we get lost in some of the details. All right. And I think there was a question about the previous example. When we were doing directed resolution, the people were talking about weights. We're talking about the unweighted version now. So the original clauses all have weight of 1, and everything we generate, whether a resolvent or compensation clauses, all of them have a weight of 1, right? So everything has an implicit weight of 1. And as I said in your chapter, there is the version with weights, but we're not going over that. Okay, let's take a concrete example, or basically do this example here and show how we're gonna get from this guy to this, all right? Which already solves the MAXSAT problem. And this is basically these clauses here. So I have not A or C, and then I have this guy, and then I have not A or B, and then the last one is not B or not C. And we're using the variable order ABC, so we're going to be doing the directed resolution on that guy. Again, this is the original C and F, and everything here has a weight of 1. So let me write again the binary thing here, so that if we have X or L1 and not X or L2, then this ends up being L1 or L2. And then here we'll have X or L1 or not L2. And here we'll have not X or L2 or not L1. Okay, everything we're gonna do is gonna be binary. So everything is gonna fit into this template here. And some of the compensation clauses will trivialize, as you will see. So let's go ahead and do this. And we will start by first resolving this with that. We're resolving on A. Now, the resolvent in this case end up being, right, we're canceling this with that. The resolvent will end up being the unit clause C. Okay, now, in principle, we should be getting 2 compensation clauses, all right? It gets a little bit tricky here because this is unit, but you may want to think of this as A or false, all right? So that you can apply this guy here. So what happens? What happens is initially I will have this guy, right? If I want to do the first compensation clause, it would be this guy or not false, which is true. Now, that is a trivial clause, so I'm not going to include it. So that is gone. And then the other compensating clause is this guy or not C. So I'm going to get basically A or not C. So there's only one compensation clause in this particular case. The other guy was trivial. Now, here's where it gets tricky, and here's where you have to remember. When I added these guys, what happens to these guys? They have to go away. They're no longer there, right? Remember, MAXSAT resolution is a transformation rule. It is basically not an inference rule. So I'm really now left with 1, 2, 3, 4 clauses, and those guys went away. Okay. Now, there is another resolution I can do on A, which is this and that. So let's go ahead and do it. And if I resolve this with that, then I'm going to get the resolvent, which is B or not C. And then I have to add 2 compensating clauses. Can people try to type what these compensating clauses are? Remember, I get this guy and I add something to it, and I get this guy and I add something to it. So I'm gonna have basically not A or B, and I'm gonna have to add something, and I'm gonna have A or not C, and I have to add something to it. So can you help me fill in what should I put in here? So this is this guy, or, and people are saying C, excellent. And that, because that's the complement of this. And then I have this guy, and I have to add the complement for this guy, and that would be basically not B. Excellent. Now, I did this, and now you have to realize what I have to do is I have to get rid of the two guys that I resolved. They're gone. These two now are gone. Okay, and that's what I am left with. Okay, I can't do any more on A. Everything, it's possible to do on A, but you're going to get complementary things. So there is no more on A. And now I will move to B. We have two more steps here. We're done. I'm going to go ahead and resolve this guy and this guy on B. And in that case, I will get the resolvent will be not C, and both compensation clauses end up trivializing in that case, right? So because you're going to have B or not C, and then you're going to have to add C, that trivializes. And similarly, if you take this guy and then you have to add C to it, then it also trivializes. So I'm only getting this guy. And remember, I have to take these guys out now, right? Because when I do MAXSAT resolution, it's a transformation rule, not an inference rule. Okay. You shouldn't be able to do any more on B. And then the very last step here will be doing this on C. And then I will get false in this case. And once more, these guys go away. So the final outcome that I have from this process is basically false, one empty clause, and then the two clauses, not A or B or C, and the other clause is basically not A or not C or not. And this is the part that we called gamma, and that problem is solved. A minimal cost of 1, and then every instantiation that does satisfy these two clauses is guaranteed to have a cost of 1, and every other instantiation will have a greater cost. And as we mentioned, there are 6 instantiations that satisfy this, and they all have the optimal cost of 1, and 2 others have a cost of 2. Okay, folks, so this is all what we wanted to say about MAXSAT resolution. As you saw, this is pretty interesting technique, and we will talk more about this later in terms of applications. And what we're going to do now is, as I said, start another part of our discussion. We're going to go ahead and transition into the second foundational part, and we're going to do this by linking to some of the applications on probabilistic reasoning. Now, I will be switching to PowerPoint slides next. And in fact, for the next few lectures, we will be using PowerPoint for that. So you need to give me just a second here to get rid of the whiteboard and upload the PowerPoint slides. Okay, so what we're gonna do next is basically show you how we can use Boolean logic not only to solve SAT, but to solve problems beyond SAT. Now, SAT is the prototypical problem for the class NP, and this is considered to be a very important class. It did receive a lot of attention, but a lot of the interesting problems that come, in particular in AI, computer science more generally, are beyond NP. And what we will see is that our interest in this course will be in these 4 complexity classes. So there is NP, which you know about. There is a class known as PP, which includes this guy. And this is a class that includes problems of interest to probabilistic reasoning. And there is the NP to the PP, and then there is PP to the PP. Now, we will look at these, and you'll get a very good feel of these complexity classes. And in fact, today, we will look at probabilistic graphical models, in particular, Bayesian networks, and we'll show you 4 problems on these probabilistic graphical models, each of which is complete for one of these classes. So they correspond to these complexity classes, and these would be among the things that we would be interested in solving. Now, the interesting story, it turns out to be that for these complexity classes, the prototypical problems, prototypical problem is a problem that is complete for that class, but it's also representative. So if you were to pick up one problem for the class NP, it would be what we would call the prototypical problem. So for NP, it's called SAT, right? For PP, NP to the PP, and PP to the PP, each one of them has a prototypical problem as well. And all of them end up being problems on Boolean formula. And we will check them out. They're pretty simple, as you will see. So the point is, for each one of these complexity classes, the prototypical problem is actually a problem on a Boolean formula. Now, what does that mean? That means, in principle, if you want to solve problems, at least the 4 that we talked about here, you can go and reduce them to problems on Boolean formula, all right? And you've already seen 2 of these that we're gonna go over. Now, then what? Then comes the second part of the foundation of this course, which is, how do I solve these problems that are prototypical on these classes that are phrased on Boolean formula? Well, we've seen, at least for SAT, how to do that. But for the other guys, we will be looking at approach for doing this. And we will find that there is a very systematic approach for solving problems on these, and that is by compiling them into what we call tractable Boolean circuits. So we will go over what that means, and there is a whole family of tractable Boolean circuits. But the idea, if you're able to take your Boolean formula and compile it into a tractable circuit of an appropriate type, then you can solve the corresponding problem in linear time on the circuit size. So the way the big picture looks like now is, as far as computation is involved, you just need to know how to solve these logical problems. And a systematic way of doing it is by compiling them into circuit of appropriate types. And if you know how to do this, then you can do a whole bunch of things. And among them, which we're going to mention today, is you can solve probabilistic reasoning problems through reduction. Okay, that's the big picture. Now we're going to do kind of a gentle introduction to this today, but we're going to be getting to these in more detail later. But I really wanted to give you some feel of things before we go delve into the second foundational part. So I need to change the color of my pen. So let's dive into this. And I want to say first a word on Bayesian networks, because what I'm going to do next is show you 4 problems on these networks that correspond to these classes, and then we'll see how much we're going to finish today. We're going to look at the corresponding problems from logic. For now, we will say basically that a Bayesian network, which some of you may have been exposed to this, some may have not, it's a probabilistic model. It has 2 components. The first component is a graph like this one. It's actually a directed acyclic graph. And the nodes correspond to variables. This is a Bayesian network that refers to a situation where we have an individual that may have a condition or not. That's the variable C. And there are 2 tests, T1 and T2, which can be used to detect that condition. Now, T2 also happens to be sensitive to gender. So, and we have this variable that we're using to indicate whether the 2 tests came out the same. Sometimes I want to tell you, well, someone did the 2 tests and both came out the same, but I don't want to tell you if they both came out negative or both came out positive. Okay, so you have this graph. The nodes represent variables. You can think of these edges as kind of representing causal influences. And to finish the specification of a Bayesian network, you have to give these probabilities, which are shown in this table. Basically, for every variable, you have to tell me what is the probability over that variable under every instantiation of its parents. So if you look at the condition, which depends on gender, you end up doing that using this table here. So look what happened here. Actually, I have kind of two distributions here. For a male, given that the person is male, then the distribution over C is this, okay? Have the condition, does not have the condition. For female, it's this distribution. And this table here is known as a CPT, or a conditional probability table, okay? So this is a conditional probability table. And I need to have one of them for every variable in the Bayesian network. Now, for gender here, there is no parents, so I'm just giving you one distribution. And let's look at T1. T1 is conditioned on the condition that would be this guy. Again, I have two distributions. If the person does not have the condition, does have the condition, then this is the distribution on the test came out positive versus negative. And this is if the person does not have the condition, then that's the distribution and so on. And you can see for T2, it depends on both S and C, and on the gender and on the condition. So let me ask you a question. For this CPT here, for this variable, how many distributions are embedded in this table? 4. Very good. Because for every combination of S and C, I do have, so this is one distribution, this is another, this is third and fourth, okay? And you can see for this variable here, which effectively is checking whether T1 and T2 agree with each other or not. I also have basically 4 distributions, but these distributions are 0, 1. Because this is more like this CPT is encoding like a logical constraint. Okay, now this is the Bayesian network. This is how it looks. Now this Bayesian network specifies a distribution over all variables. So I have 5 variables in this case, and with 5 binary variables, there is 32 possible instantiations. And this Bayesian network assigns a probability for each one of these instantiations. So it does give you a joint probability distribution over the variables S, C, T1, T2, and A. We're not going to show you now how to get that distribution. We're going to revisit this later. But for now, I just want to show you 4 problems that you can pose on these Bayesian networks. Because again, the Bayesian network is representing a distribution. So these 4 problems are asking questions about that distribution. The problem is that distribution is exponentially sized, right? So I cannot like construct it and then answer questions about it. I need to do it that efficiently, and that's where we get to the second part. The 4 problems we're going to look at are shown here on the side. The first is called MPE, the second is called MAR, and then MAP and SDP, and you'll see what these acronyms stand for. And each one of these problems, the decision version of that problem is complete for the corresponding class, which means it's hardest in that class. And again, let's see how far we're going to get today. After we finish these 4 problems on Bayesian networks, we'll show you the corresponding 4 problems on logical formulas, the one that you'll be experts on solving when you finish this class. And then as far as, again, motivation, and this will have to flow into Thursday, we will show you one reduction from probabilistic reasoning to logical reasoning as a teaser for what's coming next, so that you also see how simple this can be and how practical it can be. Okay, guys, so let's go to the problems. We're going to do basically 4 slides, 1 slide on each problem. And this is the first problem, which is known as MPE. Which stands for a most probable explanation. And what you have here is a screenshot of, this is actually a system called SAM-IM. It was developed by our group. It's available online if you want to try it out. Some of you have tried it out actually in 161. This is the model that I just showed you. And what happens here is I have the 1, 2, 3, 4, 5 variables. And now I came and told you, look, someone took the 2 tests and they agreed. The 2 tests came out the same. I don't know how they came out, but they came out the same. And the idea is that, okay, I know the value of this variable, but I don't know the value of these 4. So 4 variables, binary, there are 16 possible instantiations. And what I want is the one instantiation that has the highest probability. Okay, so I'm trying to find the instantiation of all variables that has the highest probability, and that's known as MPE. And if you look in this screenshot, we're getting back that this is an MPE. Now you could have multiple MPEs, right? You may have multiple instantiations that attain this highest probability, and this is one. It's saying that this is a female that doesn't have the condition and on whom both tests came out negative. And this is the probability of the MPE given that piece of evidence. The evidence here is that agreement, the two tests came out the same. Okay, so this is basically the MPE. Now, the decision version of this is when you go and say, I give you a number and I say, is there an MPE whose probability is greater than some P? And then here the answer is yes, no, right? Decision problems are yes, no problems. So the decision problem here is NP complete. And in fact, when we get back to this later, we'll also see that you can solve these MPE problems using MAXSAT. So you can take a Bayesian network and write a MAXSAT problem. If you solve it, then you actually found the MPE, and actually that's pretty competitive. When that reduction was shown in one of the competitions, that solver based on MAXSAT actually won the competition. So it's pretty interesting. Someone is asking, does the given evidence have to be the final node of the network? No. Evidence could be anywhere. It doesn't have to be even a single node. You can have evidence on multiple nodes. In the Bayesian network. So I could have said, in this case, all I know is that the person is a male and the second test came out negative. That could be the two things I know, and that would be the evidence. And I'll say maximize the other variables. Okay, let's go to the second problem in this case, which basically is the one that is PP complete. Now, again, you know what NP is. When we go to the prototypical problem for these classes, you get a very good feel of what PP and what NP to the PP and so on. So for now, just take their names. So PP complete is the query where I'm trying to compute marginal probabilities, right? This is the problem where, like you're seeing on these bubbles, what's happening in these bubbles is that, or these squares, there is a joint distribution over all variables, right? And then I will tell you, according to that distribution, what is the probability that the person has the condition? And then you get me 45.33%. So marginal probability is when I pick some variable instantiation and say, what is the probability of that? Okay, what's the probability of C being yes? What is the probability that T2 is negative? And that problem is PP complete. So that belongs to the next class. And as you will see later when we get to, just a little bit, if you know how to do counting on Boolean formula, and in particular a variation known as weighted model counting, then you can answer these questions. You can do a reduction. You can take the Bayesian network, write Boolean formula, and then do model counting on that, and you can solve this problem. And in fact, we will show you this reduction, if not today, on Thursday. And you'll see it's quite intuitive. Okay, so this is marginal probabilities, or MAR. And the decision version here is, so this problem gives you back numbers, but the decision version, which is yes, no, is when I basically give you some number P and I say, is the probability of C yes greater than P? Then it becomes yes, no. Okay, that's the decision version here. And let's see one more. So we're gonna go to the next level now and look at another query. And this is NP to the PP. And this is known as the maximum a posteriori hypothesis, or MAP. Now, this is similar to MPE, except that in MPE, I'm optimizing over all variables. So I have some evidence and I tell you, go and find me the most likely instantiation of every other variable. In MAP, you get to choose as a user and as part of the query what variables you want to optimize over. So in this case, I do have the same evidence like we've seen before, that someone did the tests and they came out the same. So I know this as evidence. But you as a user saying, I'm only interested in these two variables, gender and whether the person has the condition or not. Now, those are only two variables. And each one of them is binary. So I only have 4 possible instantiations, and I'm looking for the one instantiation that has the maximum probability, and that's the map query, all right? And according to the screenshot, we're getting one map solution, which is that this is a male that doesn't have the condition. Now, you're probably now wondering, well, let me ask you a question first. If you have an engine that does map, can you use it to do MPE? So the only thing is you have an engine that does map, can you use it to MPE? And someone is saying, yes, go ahead and choose all of your variables as your map variables. Okay, and this is correct. Then you probably are wondering and saying, but wait a minute, this sounds a little bit weird. So the first guy is NP complete, and this is NP to the PP complete. And there is a class that sits between them, PP. So you're kind of suggesting this is way more difficult than the other guy. So if I optimize over all variables, that's easier. Or if I optimize only over a subset of the variables, the problem gets hard. What's going on here? Well, when we look at the prototypical versions of this, you'd see that, but the hint here is in Bayesian networks, computing the probability of a full variable instantiation is easy. So if you go and fix the value of every variable and say, what is the probability of that? That's easy. It can be done in linear time. But if you only are interested in the probability of a partial variable instantiation, that's actually hard, right? And I'm searching for a variable instantiation that has the highest probability. In MPE, the candidates I'm looking at, evaluating them and computing scores for them is easy. In MAP, computing scores for the candidates is hard, all right? So that's basically why you, even though one is a special case of the other, this is a lot more difficult. Okay, so let me show you the last problem we're gonna look at, and that is gonna be PP to the PP. That's even more harder than this. And it looks like we'll have to gonna end it at that and then look at the prototypical problems and an example reduction next time on Thursday. This last problem is known as the same decision probability, or SDP. Now, the first few problems, MAP, MPE, and MAR, they've been around for a very long time. Actually, all of these were in Yuda Pearl's book from the 80s on Bayesian Network. The SDP is actually relatively recent. That's about 10 years ago. Actually, our group introduced it. And it is exemplary of computing expectations. Let me explain it to you. And it's have actually quite a bit of applications. So what we have here is a Bayesian network. It's a different one now. This is meant to detect pregnancy. And you have 3 tests that you can do: urine test, blood test, and scanning test. And typically, these kind of probabilistic graphical models are used like classifiers in the following sense. You get a patient and you say, all I know is that the scanning test came out negative. And then what you do, and you say, is the person pregnant or not? And then you go and compute the probability over pregnancy, and then you usually have a threshold. In this case, we're using a threshold of 90%. And then you say, is the probability of pregnancy greater than or equal to that threshold? If it is, then you declare the person as pregnant. Otherwise, you say, no, they're not pregnant. So what's happening here is I'm using the probabilistic graphical model to implement a classifier, and this is known as a Bayesian network classifier. So the idea here is, in this particular case, and now we're getting to the query. So I made a decision. I have a patient, and that patient, all I know about them is that the scanning test came out negative, and I classified them as not pregnant, right? Now, what I can do in this case is just settle and say not pregnant, or I can go and do these extra tests. So there is urine and blood, right, that I can do. And the question here, and that's the SDP query, what is the probability that my decision of no will stay the same after I have observed these 2 additional tests? Right? I want to try to evaluate, is it worth obtaining that information? And that's the same decision probability. The probability that the decision will stick, or the probability that I will make the same decision after collecting these variables. So just like MAP, you have to tell me what am I computing the SDP over. And in this case, you're telling me compute the SDP over these 2 guys. And the SDP here ends up being 78.7. So almost 79% chance you will not change your mind. Given a negative scanning test, if you go and collect blood and urine, basically almost 79% chance you'll still classify this person as not pregnant. So it is actually some kind of an expectation of a decision. It has, you can imagine, quite a bit of applications in terms of value of information. People have even used it recently to try to optimize classifiers, like maybe some of the features are not as helpful. They can be thrown away without really impacting the behavior of the classifier and so on. Okay, so this is PP to the PP, and those problems can all be solved by taking the Bayesian network, writing out a Boolean formula and solving a logical problem on the Boolean formula. Now, these are the Boolean problems that are prototypical for these complexity classes. So again, we will have to go over them next time and show you a particular reduction, but let me just orient you a little bit. We know SAT, okay? This is satisfiability. If you have a box to do SAT, then you basically efficiently, then you own that particular class. And then there are variations on that. There is something called MAJ-SAT. And then there's something called E-MAJSAT, and then there is MAJ-MAJ-SAT. Okay, they look funny names, but when you look at the description of the problems, they make sense, and you will see a very systematic graduation from one to the other. Once more, they're all on Boolean formulas. However, some of them require further information beyond the Boolean formula. For example, the last two guys require a split of the variables of the Boolean formula into two sets, X and Y. They need that to be able to solve the problem, and so on. So what will happen next time is we will start by describing these four problems, and you'll see they're pretty simple and intuitive. And then we'll just show one reduction from Bayesian network to one of these problems that show you very concretely the whole cycle of how things work. The only thing that will be missing is how do I solve these guys, all right? And that's what we will be filling in. Now, you know quite a bit about SAT. And in the second foundational part, the technology that we'll be developing will show you how to solve these in a systematic way. And once we do that part, then we come back and talk about way more applications to explainability and learning from data and knowledge and so on. But again, I hope this part that we started today and we're going to end on Thursday before we get into the second foundational part gives you a very good idea of you know, the concreteness and the usability of all of this. And let me mention one last thing here. And I mentioned this before, that what we did on SAT is not just only relevant to SAT. So when we do the second part of the foundation and talk about tractable circuit and compilation, we're going to find the SAT techniques are going to be basically integral to how we do things there from a computational point of view. So I think this is all I want to say for today. We will finish this particular story on Thursday. So I wish to thank you, and I will see you on Thursday.